This lecture will cover the alkenes. These are hydrocarbons containing a double bond. Realize that we have in a sigma mode, i.e. two sp2 hybrids are overlapping in an axis, and the remaining p orbitals overlap pi bond. The map shows that it's quite red in the central part of the molecule, meaning that we do have high electron density, which is telling us that the molecule is a Lewis base, i.e. electron donor. One of the principal reactions that occurs with these alkenes are, of course, that of electrophilic addition, and we will probe these later on down the road. Or ethene large quantity of industrial products. Two hybridization becomes apparent when we structure are close to that of the idealized 120. In this case, we do have a double bond, and so the bond length is much shorter than the corresponding alkane at 133 picometers. Alkenes show 1 degree of unsaturation, and what we got to remind ourselves is that the parent alkane has a formula CnH2n plus 2 for acyclic compounds. In the case of the alkene, we have a formula of CnH2n. This is for an acyclic alkene. Degree of unsaturations will dictate the number of multiple bonds that we have or rings. For example, we have a molecule C6H10. A cyclic alkane is C6H14. What we then do is we calculate the hydrogen deficiency by subtracting this formula from the parent alkane, and what we find is that we are 4 hydrogens deficient. For every 2 deficient hydrogens, we have a degree of unsaturation, and therefore with 4 hydrogen we divide it by 2, and our result is 2 degrees of unsaturation. A number of isomers that I can think of, are these fellas, where we can either have a C6 species with 2 double bonds, or C6 species with a triple bond, or we could have a species with 2 rings, or a ring and a double bond. For example, hexene, cyclohexene, would have a degree of unsaturation within the ring and a degree of unsaturation from this double bond. You can see here, for example, the degree of unsaturation can be easily calculated by the hydrogen number in the saturated species minus the actual hydrogen number 2. The nomenclature of alkenes are slightly different from those of alkanes because we do have a double bond that is not free to rotate. And so we end up with cis and trans isomers. And furthermore, we also have to think about E and Z isomers. Herein, we have a common species such as 2-hexene. You can see that we're using numbering possible, and therefore this fella here, for example, which is got a 7-membered chain as a long carbon chain, has a methyl on 5, hence 5-methyl. The alkene is on 3, hence 3-heptene. We also have other common nomenclatures, such as telling the reader that we have a vinyl, which is if we have a group directly attached to a carbon of the double bond, then it's called a vinyl compound. If we have a carbon attached to the double bond followed by a group, then we know that we have an allylic system, an allylic group. The carbon itself here is an allylic carbon. On to cis and trans. If we have two groups on the same side of the double bond, then we say we have a cis compound. If we have the two large groups on the opposite side, then of course we have a trans compound, transalkene. Why? Because there is no free rotation through the double bond, and so the cis and trans alkenes are what we call geometric isomers. So herein, for example, you can see that both the ethyl group and ethyl group of the cis-2 pentene are on the same side of this double bond. Hence, we have a cis-2 pentene. Here we have the ethyl and the propyl opposite of the 3-heptene, and so we have a trans species. Not all alkenes will have just two groups on them. We also have to take in consideration groups that has more, alkenes that has more than two groups on them. And herein we use the E and Z designation. And we use the Kahn-Ingold prelog to determine the priority. So if the two highest priority groups are on the opposite side, say that the species is engaging. If they're on the same side, then of course they are Zusammen. For example, herein you can see that we have on carbon 2 of the alkene, so it's 1, 2, 3, 4, carbon 2 of this alkene, you can see that we have the methyl being of a greater priority than the hydrogen. It's bigger. And so that is the species that we have to focus on. In the case of the carbon 3, then the chlorine has a larger molecular mass than the carbon 4, and so that is prioritized over that ethyl. And so therefore the chlorine and the chlorine on carbon 3 and the methyl on carbon 2, are the highest priority groups effectively, and so therefore this is a trans species. They're on opposite sides. Or should I correct myself and say they're E's? In the case of the second molecule, you can see that both the methyl and the chlorine are on the same side, and so they are Z's. So this is Z3-chloro-2-pentene. Could you name the following? What about this? Could you, well, let's try. I would advise to pause right here. And so we have a carbon chain that is 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon in length. And so it is a none, so we can get rid of that fellow. We have a alkene starting at carbon 3, and so we can get rid of this 4 nonene and this 6 nonene. And so we're left with these two fellas, where obviously alkene is on. Now if we move on, we will notice that we either have the option of the E or Z. And if we look at carbon 3, we'll note that the ethyl group is of larger priority than the hydrogen. And if you look, then you can see that this pentyl group is larger than the ethyl group here. So these are our two largest groups according to the Kahn-Prelude rule. And so therefore this, and because they're on opposite side of the alkene. Let's look at the physical properties, namely the boiling point and melting point. And these are due to the dipole of the compound. Yes, you can see that in the case of the cis moment is higher than that of the trans. The higher the dipole moment, then of course the greater the boiling point. So if you note here, for example, this is cis or Z, and this fella here is trans, and the cis larger dipole moment, and therefore the highest boiling point. Stability of alkenes can be evaluated by the heat given off on hydration to give the alkane. So here we have a series of butenes that hydrogenated in the presence of platinum to give butane. The higher G of the compound, the more unstable it is. When it is hydrogenated, then it will give off more energy. So it is an exothermic event. And so the more energy being given off, the more unstable that compound is. Butene, 1-butene, being that it is monosubstituted, is less stable than both cis-butene and trans-butene, which are disubstituted. This is due to hyperconjugation. The more substituted an alkene, the more stable it is. And as you can see, for example, here, in order of stability, heterosubstituted is the most stable series of alkenes. We also note that the energy given off by the trans alkene is less than that of the cis, meaning that the trans 2-butene is more stable than the cis. This is due to steric repulsion. You can see in the case of the trans, the two groups are quite far away, while here in the cis, the two groups have an amount of interaction with each other, and so it destabilizes the compound. And so the cis is less stable than the trans. See this in the graph of when we hydrogenate. Now we move on to the synthesis of alkenes. Alkenes are synthesized via two methods, or principally two methods. That is dehydrohalogenation of alkyl halides or dehydration of alcohols. The former can take place by a bimolecular event or a unimolecular event. The latter is only via a unimolecular event. You can see that we can use a strong base to eliminate this hydrogen halide from the alkyl halide to give the alkene, or we can use a strong acid, usually concentrated sulfuric acid or concentrated phosphoric acid, to eliminate water from the alcohol to give us the alkene. Realize that in the basic events, you can have either a small base or a large base. The smaller base generates the more highly substituted alkene, which we call the Saytzeff product. In contrast, the larger the base, we generate the Hoffman, or the Hoffman product dominates. Here you can see it's 72% using oxide. Herein we can see this substituted cyclohexane and elimination with the sodium methoxide realizes the tri-substituted alkene, as the major. However, if we use the larger tert-butoxide, then the di-substituted alkene, which is that dominates. The mechanism is an anti-periplanar mechanism, and we'll focus on that later, but it's a one-step mechanism, i.e. mechanism going by just one transition state to generate the alkene. In case of the dehydration, this is a unimolecular elimination, E1, and the mechanism is quite simple. We protonate the alcohol from acid to realize water as a good leaving group. Elimination of that water, it's a unimolecular dissociation, realizes a carbocation, which can then be removed. The proton can then be eliminated to realize your alkene. The rate determining step is the rate determining step is here. To form the carbocation. So to summarize, we can eliminate water from alcohols, we can eliminate from alkyl halides, but we can also partially reduce alkynes to give the alkenes, and we'll talk about this later when we work with them. So let's look at the reactions of the alkenes. And as I stated to you before, the primary reaction is that of electrophilic addition. Mind yourself that the addition reaction is when two products come together to form one. In this case, we've added hydrogen bromide to the alkene. The reaction is a conversion of pi bonds to two sigma bonds, and therefore it is energy favored, meaning that it's enthalpically favored. The mechanism, of course, we will go through. The selectivity, i.e. the orientation of how this hydrogen bromide adds to the double bond, can be seen in this illustration, where the bromine is located on the more substituted carbon. The mechanism itself can be syn or anti. The mechanism of can be syn or anti, or we can have a case where there's no preference. Herein, we have a question: which of this following is an example of the Markovnikov rule? The Markovnikov rule is where the halide, if adding an alkyl halide, they hit substituted carbon. So could you guess or work which one this is? I will pause right here for you to work on this problem. You'll note that in the case of A, the chlorine is on the least substituted, and in the case of C, the same thing. The chlorine is on the least substituted species, is added to the least substituted species. However, in the case of B, the chlorine is on the more substituted species here. So our answer is B. The mechanism is quite simple, yet the electrophile will approach a keen. In the case of the hydrogen halides, and of course the more positive hydrogen is what attracts the electrons from the double bond, and that will generate our carbocation, which will then be attacked by the halide. Mechanism, of course, you can see where there's an attack on the hydrogen halide, followed by the formation of the more substituted carbocation, is then further attacked by the halide to give us our Markovnikov product. a cyclohexene, methyl cyclohexene, with iodochlorine. Iodine, of course, being less electropositive than the chlorine, is the electrophilic part of that molecule. So nucleophile, i.e. the alkene, will attack electrophile, and there's a possibility of two carbocation, tertiary carbocation, or this primary carbocation. And it stands to reason that the tertiary will dominate. If you look at the energy diagram, you can see that the Markovnikov carbocation, i.e. the more substituted carbocation, is more stable. And according to Hammond's postulate, Hammond stated that the transition state here is much of the Markovnikov species. Stability therefore realizes a activation energy which is much less. This activation energy being less will therefore realize that this is the dominant route that is being taken. The stabilization of this carbocation, of course, is due to hyperconjugation. So in this case here, where we have propene, you can see that this secondary carbocation is more stable than the primary carbocation. Therefore, this is the species that dominates. Therefore, this is the route that we take. And so, therefore, this is the Markovnikov product. This is the major product. So I could ask a question like this: which of these will react faster with HCl? Hint: the species that produces most stable carbocation when it is protonated. Pause right here and you'll work on this. Excellent. You will note that in the case of A, there are two possibilities here and this is the more substituted carbon, but that would only generate a secondary carbocation. Here, this is the more substituted species, that will generate a secondary carbocation. Same thing here, there's possibility of two secondary carbocations. That's here and here. Here is also secondary carbocation, and here is secondary carbocation. Because we really want, for example, here you can see that you can add a proton here with the ethyl. There's another proton that was there before. That will give you the secondary carbocation. However, if you look closely at D, it has 1, 2, 3, this carbon with 3 carbons attached to it, so that those are 3 groups, and so the resulting species would be a tertiary carbocation. So this will give you the most stable on protonation, i.e. reaction with HCl, and so this will be the fastest. We can also predict products like this, for example, and that is, of course, you can see that Markovnikov dominates. In the case of the stereochemistry, you realize that on protonation, we end up with a carbocation that is planar, meaning that, yeah, it's achiral. My bromine or my halide can attack both above or below the plane of this molecule, of this carbocation. And so we end up with a racemic mixture. Let's talk about carbocation rearrangement. Here you can see, for example, if I protonate, the carbocation in this case is secondary. But if on 2 hydride shift, meaning that assuming this is carbon 1 as carbon 2, then the hydrogen moves from carbon 2 to carbon 1, and we end up with a tertiary secondary carbocation in this rearrangement. Carbocation here dominates, it's quite nice. Yes. No tendency to rearrange here. However, something like this, where we generate this secondary carbocation, can shift. So now we have this alkyl shift to generate a tertiary carbocation, which can then be attacked by to this alcohol. Driving force is moving from a secondary to a tertiary carbocation. If there's a possibility that it can rearrange, it will rearrange. This is the nature of the beast. So here we can see an hydride shift to form a tertiary carbocation. Second case, you can see that we started off with a secondary carbocation, another hydride shift to form the tertiary carbocation. Here is something interesting that happens because you can see that we start off with a secondary carbocation being formed, but then we have this ring expansion by an alkyl shift. So this pair of electrons here that's part of this bond, that consists of this bond, moves to the carbon 2, and then we have the tertiary carbocation. Four-membered ring to a 5-membered ring, the 5-membered ring, of course, being less strained. And so there's a huge incentive for this rearrangement to occur. We're going to look closer at the mechanisms of electrophilic addition, and so we'd advise you to take a break at this time. There's quite a few reagents that we got to keep in mind, and so it takes a lot of practice, a lot of reviews to remember these reagents. But the mechanisms of these alkenes, principally electrophilic addition, and we will go through these, yes, one by one. The first one we're looking at is the addition of bromine, any pure halogen. Right. In this case, fluoride is a bit too reactive and iodine is not pleasant. So we're sticking with the bromine and chlorine. The mechanism realizes a trans stereochemistry of the orientation of the bromines. So the bromines are on the opposite side of the ring. Look carefully. The mechanism looks like this. We attack the bromine, which is the electrophile, to realize this species, which is bromonium cation. Note, yeah, it is a species, three ring. So sterics, the bromine will, or on the opposite side of our ring, not this side, because the bromine is too bulky. The result is we have this anti-addition, or this anti-attack, which results in this trans arrangement or this anti-arrangement. So it's a trans dibromide, not cis. That this fella is your answer. It's not. Your answer is, of course, two trans species. Good. In the case of bromine in water, an interesting species results. The result of this reaction is the anti-addition of the halide in OH, and it's called the Halohydrin reaction. The first part of the mechanism is the attack on the halide to form the bromonium. Water, due to mass effects, water will then attack the Markovnikov center, i.e. the most substituted carbon of this bromonium species. So this anti-attack will result in this trans arrangement of the precursor OH, which you can then deprotonate to give you your product. So it's a trans arrangement or anti-arrangement of the OH to the bromine, the halohydrin reaction. There's a simple test for alkenes actually, and this is to react bromine with with the substrate. If the bromine disappears, know that we have a double bond present in the mixture. Herein, I asked you to predict the products. Pause right here and try to figure out what correct response is. Of course, you realize by now that it has to be a trans arrangement, and you can see that both B and D are got the anti-arrangement of the bromine to the other variations. Of course, we could use alcohols to form some type of, and of course that alkoxide group would be anti to the bromine. Now there's also the addition of water to the alkene. We call oxymercuration. And this is terribly important because it, when we use an acid to add water, it's a very harsh reagent. On the other hand, the mercuration process is a. In addition to this, because when with the mercuric acetate, we realize a species similar to the bromonium, the possibility of a rearrangement is not get a carbocation that can rearrange. We get this ion. Typical of the mercurium ion or any one of these species in here. Attack of the water occurs at the Markovnikov position to realize the anti-arrangement of the OH to the mercuric acetate. We cannot leave this product with the mercury attached to it like that. That's not our final product. And so what we do is we add sodium borohydride to cleave mercury substrate to realize is being resulted in anti-addition of this OH and H across the double bond. It is a Markovnikov species because the OH is on the more substituted carbon. The next one we need to look at is that of hydroboration. We say we have an anti-Markovnikov addition of water, and it's a mechanism in the sense that we use the borane with followed by basic peroxide, and OH and the H of the water that we added are on the same side. This is a syn addition compared to the anti-addition that we saw previously. So note the transition state that occurs once you add the borane. The boron is sitting on the least substituted carbon because of the sterics. So once this transition state collapses, we end up with this product where the boron and the hydrogen that we added from the boron across the double bond, yeah, is now on the same side. It's added on the same side, same side. But like the previous example, we cannot leave this boron side species to generate the desired product. Then, of course, we react this compound with basic peroxide, and that OH minus will substitute the boron to realize our alcohol. Here's the syn addition. So both the OH and H of the added water are on the same face of the molecule. Say that it's anti-Markovnikov because the OH is on the least substituted carbon. Here's a clearer view. Try to predict this product. For a solution to this, we will go back to the previous slide. And if you look at the previous slide, you would realize that when we added the boron to the double bond, it was on the opposite face of the methyl. It was on the opposite face of the methyl, meaning that once we substituted the boron with the OH minus, the OH is on the opposite side of the methyl. So let's go back to our problem and note that this is our double bond. It is anti-Markovnikov addition, and so the boron should result. So if we add here, the transition state should look like where the boron is here, the hydrogen is here on the more substituted carbon, and of course this shows the double bond breaking. This is our transition state. But remind yourself that this bond here is opposite side to this. So when we do treat it with the hydroxide, the basic hydroxide, expect that this will be on the opposite side. This OH will be on the opposite side of the methyl. So we're looking for any product where the methyl is on the opposite side of the hydroxy group. This is not an anti-Markovnikov product, and C is not an anti-Markovnikov product. Sorry, this is not an anti-Markovnikov product because the OH is of the more substituted carbon. Herein, this is not an anti-Markovnikov product either. So we're left with these options, and you can see that here the methyl is opposite, and here also and methyl is opposite. So both of those are acceptable. Other reactions that we can think of uh, is the addition of um, this carbon dihalide in this carbene reaction. So we add chloroform with KOH, so it's basic chloroform, and we end up with this rather strained cyclopropane ring with two halides on them. Or we can use this diiodomethane in the presence of a zinc catalyst, and this is called the Simmons-Smith, where we have the naked cyclopropane. This is, of course, a syn mechanism, and so stereochemistry is retained. So in this case here, the first case, we have a transalkene, and we end up with a ring where the groups are trans, i.e. on opposite side. In the second case, we have a cisalkene, and you can see that we end up with a ring where two groups are on the same side, i.e. cis. The mechanism is quite sophisticated, and I advise you to look in the notes and make sure you get it. Other mentions, of course, is hydrogenation. Yeah, using a heterogeneous catalyst like palladium, in this case palladium black. And you can see that it is a syn mechanism. But not only that, you can see that there are some sort of selectivity that occurs. Because it's a heterogeneous catalyst, then the hydrogenation takes place on the least steric phase. Here is another reaction that's terribly important to us. This is the formation of oxyranes. And in this case here, we're using a peroxycarboxylic acid. In this case, we have this peroxycarboxylic acid called MCPBA, which stands for metachlorobenzoic peroxybenzoic acid. And again, it is syn addition, but it's a syn attack, I should say, and the result is an oxyrane ring where the stereochemistry is retained. Formation of these epoxides are terribly important to us, and we will focus on this reaction later on when we do ethers. But herein, if we treat this with an acid, we end up with a diol. But not on any diol, we end up with a trans diol. Here are a few other products that we can get from this. And when we do start looking at epoxides, we'll focus on these more. In the case of treating the alkene with osmium tetroxide or cold dilute permanganate, we end up with syn diol, the syn diol or the cis diol. Remind yourself that here we had the trans diol, And in this case here, we have the syn diol. Hot permanganates, i.e. severe oxidation, or using ozone, we end up with cleavage. So in this case here, cleavage reductive conditions, this is dimethyl sulfide, sometimes there's some zinc present. We end up with cleavage of our alkene. So we have cleaved, we have broken the carbon-carbon bond to give us carbonyls. In this case here, of course it's reductive conditions, we end up with ketones and aldehydes. Herein, for example, we have cleavage here, and so because it's a ring system, the alkene is present in a ring, resulting molecule, has both carbonyls present in it. Herein we have two double bonds, and so we end up with, let's go to this cleavage here and here. Molecule, two molecules, and three. You can see that 3 is a ketone, 1 is an aldehyde, and 2 has 2 different carbonyls on it. Note, on the oxidative conditions, so here we got peroxides, instead of the dimethyl sulfide, this hydrogen is not retained. In fact, on cleavage, we end up with the hydrogen now being replaced by an OH, and so this result is a carboxylic acid. So we end up with a ketone and a carboxylic acid. So if there is a terminal hydrogen, or hydrogen present on your alkene, I should say, then ozonolysis on the oxidative conditions will generate carboxylic acids. Same thing will occur with hot potassium permanganate. And this one we did not go through, but this one here we'll talk about when we start to do radical reactions. But when we use NBS, which is N-bromosuccinimide, a reagent that's used for bromination, we brominate the allylic portion of our molecule. So none of these products are the product that we'll generate is bromination on the allylic carbon of the alkene. The alkene is retained. Now, just a reminder of how we study functional group chemistry is you got to ask yourself why they react. And then, of course, note the mechanism, especially the arrow pushing, and note the thermal and the kinetics behind it. Reagents vary, but they usually can be remembered with strong practice.